Hello, my name is Sharon Chopper and today I am presenting our work Zero Transfer GPU Pipeline for Real-Time Wildfire Aerosol Forecasting from GeoES Satellites. Before getting into the technical details, it is important to set the context. Wildfire smoke can change rapidly within minutes, and short-term prediction of its movement is critical for timely decision making. This work focuses on enabling reliable forecasts over short-term horizons, which require rethinking the entire compute architecture from the ground up. Wildfires are not a local problem. The smoke they generate can degrade air quality hundreds, sometimes thousands of miles away from the fire source. We're talking about particulate matter that affects respiratory health, disrupts aviation, and can stay suspended in the atmosphere for days. Real-time aerosol tracking is therefore critical for emergency management, public health advisories, and evacuation planning. The good news is that we have excellent satellite data available already. The GeoES 16 and the GeoES 17 geostationary satellites produce aerosol optical depth or AOD retrievals every 5 minutes over the continental United States. That is an extraordinarily fine temporal cadence for atmospheric monitoring. The challenge, however, is on the compute side. Prior state-of-the-art methods, including physics-informed statistical models, are computationally too slow to meet the 5-minute window. They prioritize numerical accuracy, but they were simply not designed with real-time constraints in mind. And while machine learning systems can be fast, they typically lack physically interpretable dynamics. You don't really know why the model is making a prediction, and in an emergency management context, interpretability is not optional. So we are faced with a gap. We have rich high-frequency satellite data on one side and slow, physically grounded models on the other. The question our work asks is, can we close the gap without sacrificing accuracy? Our 5 core contributions are: first, we present a zero-transfer GPU pipeline, meaning all data stays on the GPU device throughout the entire computation. There are no PCIe transfers between processing stages and no round trips to the CPU memory. This is architecturally significant, and I'll explain why shortly. Second, we develop a library of CUDA statistical primitives, GPU-native replacements for the R functions that form the original pipeline. This include KNN imputation, optical flow, spectral smoothing, and the critical inverse Wishart sampler that was a major numerical bottleneck. Third, and most importantly, we achieved real-time execution. The total pipeline runs within 23.4 seconds, comfortably fitting inside the 5-minute GeoES acquisition window. Fourth, we deliver a stable Bayesian inference through a corrected Gibbs sampler initialization that actually improves accuracy over the original R baseline, not just matches it. And fifth, the system is built with a modular design where each stage is independently testable and reusable, making it straightforward to swap in future improvements. Now, let me give some background on the underlying physical model and the pipeline architecture. The mathematical foundation is a physics-informed Bayesian state space model. I will walk through the 5 phases at a high level. Phase 1 is data ingestion. We take GeoES 16 and GeoES 17 AOD retrievals at 5-minute cadence and project them onto a 60 by 60 spatial grid covering the western United States. Any missing data due to the clouds or sensor gaps is masked. Phase 2 estimates the physical field. We use Lucas-Kennedy optical flow to estimate wind velocity and compute spatially varying diffusivity from the velocity strain rate. These fields drive the atmospheric dynamics in the model. Phase 3 handles spectral representation. AOD is decomposed into Fourier basis tourniqueted at wave number 20 in each direction, giving us 400 spectral coefficients from 3600 spatial cells. The transition matrix G is computed as the matrix exponential of a physical operator that couples velocity and diffusivity. This is the most expensive step in the pipeline. Phase 4 performs Bayesian inference via a Gibbs sampler with forward filtering backward sampling known as FFBS and Kalman filter updates. The hidden state lives in R to the power 800, encoding spectral coefficients from both satellites. Phase 5 generates the forecast. We propagate the posterior state mean forward k steps using the repeated application of transition matrix, yielding short horizon AOD predictions. This is a rich and well-grounded physical model. The problem was that running it took nearly 6 hours in R, and this is what we set out to fix. Before presenting our full GPU solution, let me describe the intermediate step, a hybrid R-CUDA pipeline that we built as a first iteration. The original R pipeline took 5 hours and 50 minutes to process just 40 dual satellite images. Profiling revealed that the bottlenecks were severe and concentrated. The transition matrix computation alone consumed 73% of the time, which is 4 hours and 15 minutes. The Gibbs FFBS iteration accounted for another 12%, and the processing with optical flow took up to the remaining 15%. Our hybrid solution ported these main bottlenecks to CUDA-C while preserving the existing R workflow structure around them. We ensured numerical correctness to within 10 to the negative 6th, and the result was dramatic. The transition matrix saw a 1019 times speedup, and the Gibbs FFBS achieved a 486 times speedup. The total wall time dropped from 5 hours 50 minutes to 12 minutes 19 seconds, which is roughly a 28 times improvement overall. But 12 minutes still does not meet a 5-minute GOES window, and importantly, this hybrid architecture had a fundamental flaw. PCIe transfer between the R and the GPU at every stage boundary created overhead, which prevented streaming interface and left real-time operation out of reach. That understanding motivated our full zero transfer redesign. Let me now walk through our full GPU pipeline, which eliminates all host-to-device transfers by keeping the entire computation on device. Stage 1 is regrading. Raw GOES data comes in scan angle coordinates with irregular pixel spacing. We launched 3600 threads organized as 15 blocks of 256 to map incoming pixels onto our 60 by 60 geographical grid in a single pass. This handles anywhere from 5000 to 15,000 incoming pixels per time step. The key results are exact match with R, and execution time drops from 104.6 seconds in R to 0.026 seconds on GPU, a 4000 times improvement. Stage 2 is KNN imputation. Between 0.5% and 8% of the grid cells may have missing values at any given time step due to a cloud masking. We fill this using GPU k nearest neighbor kernel with k equal to 10, operating on a 60 by 60 matrix loaded into shared memory with only 60 threads. The numerical error compared to R is approximately 10 to the negative 15th, which essentially is machine precision. Stage 3 is optical flow. We implement the Lucas-Kennedy algorithm with a 15 by 15 pixel window. Each pixel gets one thread, and the 3 by 3 linear system at each location is solved entirely in registers with no synchronization needed between the threads. Error versus R is approximately 10 to the negative 14th. Stage 4 is smoothing and diffusivity. We use CUFFT to compute spectral smoothing on a 60 by 60 grid upsampled to 120 by 120, followed by estimation of diffusivity from velocity gradients. This stage achieves a 1430 times speedup over R. Stage 5 is the Fourier basis. We pre-compute and store the fixed 3600 by 400 basis matrix on the GPU at initial time, then reuse it across all time steps. This avoids redundant computation and the basis never leaves the device. Error is below 10 to the negative 14th. Stage 6 is the G matrix and matrix exponential. This is the most computationally intensive stage. Computing the 400 by 400 transition matrix G as a matrix exponential of the physics operator. We use CU BLAS and CU solver for parallel reductions over 3600 cells, avoiding any explicit matrix inversion. The matrix exponential itself is computed using the scaling and squaring algorithm. Despite its complexity, this stage achieves 1356 times speedup over R. Stage 7 is observation assembly, device side scatter and gather operations using truss assemble observation matrices F1T, F2T and measurement vectors Y1T and Y2T from both satellites at each time step. Crucially, no CPU involvement is required at this stage. Data flows directly from physics computation to the Bayesian inference stage. Stage 8 is Gibbs FFPS. The Kalman filter updates operate on the 800 by 800 matrix. The full forward filtering and backward sampling loop runs on device with only the final parameter estimates, briefly touching the CPU for convergence monitoring. This stage achieves 230 times speedup. The key design principle unifying all 8 stages is the zero transfer philosophy. Data is allocated once on the GPU startup and never copied back to host memory between the pipeline stages. This eliminates PCIe latency, prevents memory bandwidth saturation, and is what ultimately enables the real-time operation. I want to spend some time on a particularly interesting engineering challenge we encountered: numerically unstable inverse Wishart sampling. In the Gibbs sampler, we need to draw samples from an inverse Wishart distribution at each iteration to update the observation noise covariance. The native implementation uses direct matrix inversion on a 800 by 800 matrix, which is O p to the power 3 in cost with p equal to 800, and it suffered from numerical instability. Near singular scale matrices caused small eigenvalues to be amplified, producing biased Kalman gain. The practical consequences were severe. GOS 17 RMSE increased by 2.3 times compared to the R baseline. Our fix was to replace the direct inversion with a Bartlett decomposition. Instead of inverting the scale matrix, we first compute the Cholesky factor once per Gibbs iteration. We then construct a lower triangular matrix where diagonal entries are drawn from chi distribution and off-diagonal entries from standard normals. The inverse Wishart samples is then recovered via two triangular solves, which are quadratic cost rather than cubic, and a symmetric rank update. This not only removes the numerical instability but also reduces computational cost because triangular solves are much cheaper than full inversion. We further stabilize the sampler by initializing the prior means as a scaled identity matrix and fixing the noise variance during the early burn-in period. The result: numerical stability restored, GOES 17 accuracy recovered, and the sample converges reliably across all 20 time steps. Now let us look at the results. I want to start with the bias field validation. If you look at this slide, you will see bias field maps from our GPU pipeline on top and from the R reference implementation on the bottom. At 4 time steps, t equal to 5, 10, 15, and 20. There are several important things to observe. First, the GPU bias field closely matches the R reference. The spatial pattern and magnitude ranks are consistent across both implementation. Second, the bias field evolves smoothly over time and remains bounded, which is exactly the behavior we want from a well-initialized Bayesian model. Third, and this is crucial, the model achieves correct separation between physical AOD signal and calibration bias. The bias channel is effectively learning to absorb systematic satellite calibration offsets, leaving the main state channel to track genuine atmospheric aerosol. This separation is the hallmark of a well-functioning state space model, and our GPU implementation preserves it perfectly. The forecast validation results are equally strong. This figure shows k-step ahead forecast error fields at horizons k equal to 1 through 4, with GPU results on top, R in the middle, and difference on the bottom row. The quantitative results are very encouraging. The mean absolute difference between GPU and R forecast is 0.092 at k equals 1 and essentially flat at 0.093 at k equals 5. This is approximately 2% of the domain mean AOD, a very small discrepancy. Critically, there is no error growth with forecast horizon, which tells us the GPU pipeline does not accumulate numerical drift over time. There is also no systematic spatial divergence. The differences are spatially unstructured and random. We carefully investigated the source of those small differences and traced them to stochastic variation between CUDA's random number generator, CU-RAND, and R's, Mersenne twistor, not to any algorithmic difference. The forecasts are verified on KNN imputed AOD at t equal 40, and there are no cloud mask gaps affecting the validation. In short, the GPU pipeline is numerically equivalent to R up to random seed differences. Looking at the stage-by-stage breakdown, regrading both satellites takes 0.073 seconds on GPU versus 243 seconds in R, a 3,332 times speedup. Velocity diffusivity estimation takes 0.319 seconds versus 457 seconds, which is 1,434 times faster. The G matrix and exponential takes 11.6 seconds versus 15,746 seconds, which is 1,356 times faster. The Gibbs FFBS takes 10.6 seconds versus 2,442 seconds, which is 230 times faster. The total pipeline runs in 23.4 seconds compared to 5.96 hours in R, and end-to-end speedup of 918 times. This comfortably fits inside the 5-minute GeoES acquisition cadence, meaning we can process each new satellite image before the next one arrives. But here is the result I am most proud of. Accuracy improves alongside speed. Our GPU pipeline achieves total MSE of 0.102 compared to 0.149 for the R baseline. The Barrett decomposition fix and the corrected Gibbs initialization are not just numerical patches. They actively make the inference better, and we went from a pipeline that was slow and slightly biased to one that is fast and more accurate. Let me close with the broader implication of this work. The architectural insight at the heart of this project is a philosophical shift in how we use the GPU. We did not accelerate an R pipeline by offloading bottlenecks to CUDA. We redesigned the entire compute graph with the GPU as the primary compute substrate, not a coprocessor. Each stage lives on device, every intermediate result stays in GPU memory, and the CPU is only involved for final output reporting. The zero transfer principle is what enables the 918 times speedup. The modular CUDA design also means individual stages can be upgraded independently. Looking forward, there are several exciting directions. Multi-GPU scaling would allow us to cover larger geographic domains or run ensemble forecasts in parallel, live GIS streaming integration in the next milestone toward operational development, ensemble Gibbs sampling would give us richer uncertainty quantification, and removing the current Fourier truncation at wave number 20 in favor of a full resolution spectral model would improve spatial fidelity. The broader version is a system where within seconds of satellite overpass, the land managers, air quality agencies, and emergency responders have a physically grounded, uncertainty-aware aerosol forecast in hand. Thank you very much for your time and attention.